Now let's dive into some more specific types of UV light disinfection technology. So can you tell us more about filtered 222 nanometer Far UVC light disinfection technology?
Absolutely. What I'd like to do is spend a little bit more time talking about UV in general. It is, a form of electromagnetic radiation. It's broken into the three bands of UVC, UVB, and UVA. And as Dr. Sliney mentioned, the reason we focus on UVC is because of its known impact on both bacteria and viruses and being able to interact directly with the RNA and DNA molecules and essentially making it so that the pathogen isn't able to replicate. And in that process, that's how we are inactivating the pathogens and reducing our exposure to them. This is kind of what's known about UVC, and UVC is their wavelengths that range from 100 to 280 nanometers. So broad range of wavelengths that are going to target both bacteria and viruses, get right at the RNA and DNA molecules. So why do we differentiate what far UVC is? Far UVC is considered to be wavelengths under 230 nanometers. And the reason we differentiate the far UVC is that it, in addition to its effectiveness against pathogens, it has a very different interaction when it comes to how it interacts with human cells. And because 222 nanometers specifically is absorbed by proteins in our cells, both the dead skin cell layer on skin and also our tear layer that covers our cornea and basically is protecting our cornea from exposure to that far UVC. This is the fundamental reason why this wavelength doesn't have the same type of potential harm that the more conventional 254 germicidal UV wavelength does. So with the far UVC, we are naturally protected from exposure to those wavelengths in the deeper layers of our skin and protected from the exposure to our cornea. To provide the guidance and looking at how much exposure we can have for all wavelengths of UV, but again, focusing on the 222 nanometers, there's an organization called the ACGIH, or the American Conference of Governmental Industrial Hygienists. And this organization establishes what are called time-weighted average threshold limit values, which are essentially doses that workers can be exposed to without adverse health effects. And these values are reported for 8-hour periods of time. So for 222 nanometers, that threshold limit value is currently set at 22 millijoules per centimeter squared. So that is the acceptable dose for this wavelength over an 8-hour period. And just to compare and contrast how that is compared to conventional 254 nanometer germicidal UV, the threshold limit value for that wavelength is currently set at 6 millijoules per centimeter squared. So these threshold limit values are very much, you could say, the math behind the biologic difference that I was describing. The ACGIH publishes guidelines, and these guidelines are adopted into standards worldwide, including the IEC 62471, which is our photobiological safety of lamps and lamp systems. And this is the standard to which UL tests germicidal UV products for the photobiological safety assessment and also certification.
Now let's bring in filters. So why is the filter such a key part of this technology, and what might happen if there is no filter, Janine?
Before I dive into the filter, I'll talk a little bit about the technology itself that is creating the 222 nanometers. Today's technology is based on a krypton chlorine excimer lamp. This is an arc discharge light source. It's employing a special chamber that's filled with those noble gases of krypton and chlorine. Operates completely mercury-free and without electrodes. And it strikes with no warm-up time, and it's a very stable light source when it's operating. But the key point here with respect to the filter is that the native spectral power distribution of the krypton chlorine excimer lamp, it has a spike at 222 nanometers, but there's a tail that goes into those longer wavelengths, 254 nanometers, 274 nanometers. And these are the wavelengths that have that greater potential for harm, and can more deeply penetrate the skin and reach the cornea. So without the filtering, those wavelengths are present in the krypton chlorine excimer lamp. So when we are able to apply the filter, we essentially remove all of the wavelengths above 230 nanometers, and we do have a very narrow band emission that is then focused on 222 nanometers. The filter technology is based on dichroic technology, using new thin film materials that provide that desired transmission and suppression bands, and it's coated on a substrate material made from quartz, which is the highest melting glass available. And as we were getting in before a little bit about the ACGIH guidelines, is that with the filtered 222 nanometers that the guideline is at 22 millijoules per centimeter squared. So if we would add in some of those other wavelengths, we need to account for those emissions as we look at the ACGIH published curve. And it would mean that you would have to reduce the output by about 25% in order to be able to use an unfiltered 222 nanometer light source. And that would mean that you would not be able to deliver, you would have essentially 25% less power to be able to target the pathogens in the space. So it greatly reduces the effectiveness, the whole reason you're installing the filtered 222 nanometer Far UVC in the first place. And in addition to that, with the filter, you're completely eliminating those more harmful wavelengths in the first place.